So, welcome everybody. This is the story of the life, part 3, the making of complex cells. So, let's just do a quick recap of what we've seen so far. This is already dealt with the transitioning of inorganic molecules to organic molecules. That's based off the Miller-Urey in the Lost City that we watch, the video that we watch about the Lost City and the whole process of first creating those organic molecules that didn't exist. And then you watch the video about how those organic molecules became the first simple cells, became those things called protocells, and how that first process came about. Now we're going to transition to complex cells. How did these eukaryotes come into existence, and how that happened to eventually lead to the complex life that we know today and we see all around us. So again, we think back to early Earth, we're thinking back to the first protocells kind of floating around in the ocean. Okay, they're not really totally alive, but they're kind of alive, about 80-20% alive. But a couple of things they could do. One, they can multiply. They can make more. They can just make more and more and more of themselves. The second thing they could do that was a symbol of whether or not they're alive is they could evolve. They could modify their structure and modify the things that their makeup, and start to modify their DNA. So they could go through this process of evolution. So eventually these protocells became bacteria. Okay, very simple organisms, no organelles, very, like I said, very ancient, simple bacteria that had the propensity to become other things. They could evolve to become other things, and they did. That evolution continued, the bacteria continued to grow and multiply, and you had a new group called archaea. So you had your bacteria and you had your archaea existing. Okay? But still, both very simple cells, no organelles, nothing to make them more advanced, still very simple. So these are kind of the earliest forms of life on the planet. As I said, they're very simple, very primitive. They're anoxic. That means that they do not like oxygen. So this means they do not, no O2. Okay, they don't like oxygen. It can kill them. They don't thrive on it. And they're prokaryotes. They are not eukaryotes. They are a simple cell. They're basically just DNA floating around in their cytoplasm with their membrane. However, one day a bacteria mutates, and it shows up. It has some different. It has some different properties. What are those different properties? Well, this mutation allows this bacteria to take energy from the sun and make oxygen out of it. So this new bacteria starts to take the sun's energy and make lots and lots of oxygen. And this is the process we know today, photosynthesis, right? We know that plants all over the place take sun's energy and they make oxygen. They produce oxygen out of it. And this bacteria is called the cyanobacteria. So these cyanobacteria still exist today. They're different. Obviously, they've changed over the course of billions of years, but they still do exist today. There are still lots of cyanobacteria floating around in the ocean. But this cyanobacteria started to thrive because, well, there was lots of sun and there was lots of energy from the sun. So it started to multiply. But when it multiplied, it led to more and more oxygen being created. Okay? Which, if you think back to what we just talked about with bacteria and archaea, the fact that they don't like oxygen. It's toxic to them. And this is toxic to all these other bacteria, and they start to die. And they'll just vanish. They don't exist anymore because they can't handle that heavy oxygen-rich environment. So more and more cyanobacteria keep growing, and they keep growing, which is going to produce more and more oxygen. And it's going to lead to problems for all those bacteria that view oxygen as something toxic to them. They can't thrive in that environment. So this leads to the first great mass extinction event in Earth's history, called the Great Oxidation Event. So it's basically the killing off of all these very primitive bacteria early on by the fact that there was now oxygen in the atmosphere. So the oxygen, the bacteria had basically choices to do one of three things. One, they could die, which we've seen a lot of them did. Okay? Two, they could go and hide. So this might be one of those vents way down in the ocean, right? Way down at the bottom of the ocean. And this bacteria might go hide down in there, and actually some of them have. And they've hidden in places where there's no oxygen. Okay? It's too far away from the Earth's surface where oxygen is thriving, and they can survive in these places in really deep, deep depths of the ocean or hidden underneath the crust. And so is option 2, go hide. The third option is they could evolve, and that's what some of them did. And some of them, their evolution was that they started to take that oxygen and converted it into the energy that they needed. So instead of oxygen being toxic for them, it actually became something that provided their energy source. So this is something that obviously they're going to start to thrive in this environment. So that new organism starts to thrive because there's so much oxygen and nobody else is competing for that resource because nobody else wants it. So this new bacteria, this new organism starts to develop further and further and further, right? There's more and more and more of them around. Right? However, another mutation starts to occur because there's still bacteria and archaea left over, okay, and they're trying to survive, they're trying to find a way, and then all of a sudden one of them mutates, and all of a sudden now it can fold its membrane. Okay, so now instead of just being a single membrane, it can kind of wrap itself up and create different shapes and structures. Okay, and why is that going to be a positive thing? Well, let's think about it this way. Well, what if oxygen starts to get near that folded membrane? So the oxygen's making its way over. It's like, I'm going to come kill this bacteria because it hates me, because it can't thrive in an environment with oxygen. Instead, what happens is this new bacteria can actually consume one of those new mutated bacteria that thrive on oxygen. So that bacteria will kind of wrap itself around it, and now all of a sudden it can handle oxygen. Oxygen comes near and it produces energy off it. So now all of a sudden this bacteria that oxygen was toxic to can now thrive and create energy in that environment. And this is a process called endosymbiosis. Basically, the swallowing, the consumption of another molecule, bacteria, one prokaryote consuming another prokaryote, and now all of a sudden it can generate energy because of the new mutation that's developed. What does this give rise to? Well, it gives rise to eukaryotes. We now have a cell here that is no longer a simple cell. It is now a complex cell because it has other material inside it other than just its DNA. So this sounds kind of cool, pretty impressive. What's the evidence though? So the evidence is this. There's two major pieces of evidence. Various organelles such as mitochondria and chloroplasts exist within the cell. And these are kind of the energy warehouses of the cell. They're the energy producers for every single type of cell. Chloroplasts in plants, mitochondria in humans, there's still mitochondria in plants too. But all of these things, they are the energy stores. And two key things about them, they have their own unique DNA, and they both have double layered membranes. Okay. And why is this important? Well, let's see. So here's our basic cell. Great, we have a nice cell. Now it has a nucleus which has DNA inside it. And it has a bunch of organelles inside it. But one thing you'll notice here, if you look at this cell, that organelle right there, is you'll see it has its own DNA inside. And you'll also notice that it has a double layered membrane. Okay? So this would be like the mitochondria. Has its own DNA and has its own double membrane. Okay? So it's almost like it's another cell that was swallowed up by the first cell. Well, how does it help prove endosymbiosis? Well, earlier, again, you had bacteria, right? Simple prokaryotes, DNA floating around inside, no organelles. You also had archaea, also prokaryotes, DNA floating around inside, membrane, but no organelles. Now then, these bacteria, they were to engulf this archaea. They would surround their membrane around that archaea. And all of a sudden now we see that we have a set of DNA inside our original bacteria, and now this may be that archaea that does consume oxygen and does produce energy off it. But the key is that the double membrane is still maintained, in addition to those two sets of DNA inside the cell. The reason the double membrane's maintained, if you think about it again, is the fact that this original cell, to swallow up that other archaea, actually had to almost wrap itself around it like this and then pinch off on the two sides. So when it does that, the double membrane here is still maintained. You have the interior membrane of the archaea, and also now this membrane portion of the bacteria surrounding it. So this is that first eukaryote. It has an organelle inside it with the distinct DNA of another cell. And we can see this today in mitochondria and chloroplasts. If you look at the mitochondria, we have double layered here. So there's a high zoom in on an electron microscopy of that. And inside here in our plant cell, it's a little harder to see. But each of these little things right here, these are your chloroplasts, and each one of those is also a distinct organelle with its own DNA inside and a double layered membrane. So all of those signs show that how this energy store came to be inside these cells is by the consumption of other simple prokaryotes by a prokaryote way back in Earth's history.